Hello everyone, this is my design for my homopolar motor. It's pretty simple, just got a magnet attached to a screw suspended from a Phillips bit. I might end up changing the Phillips bit because it's kind of unstable, kind of gets stuck in the groove sometimes. My original design involved like ball bearings and like these things. You can see the ball bearing in there, but that ended up not working because the force of friction, like just in the ball bearings, was too much for the torque of this motor to overcome. So this design is pretty low friction, so it ended up working, especially after I opted for the big battery, which provides quite a bit more current than double A's. So I'm going to connect this up, complete the circuit in a second, and it should spin. Okay, so I'm going to explain how this homopolar motor works. This is the circuit that I had built in the previous clip. I have a battery right here. I was using the 12-volt car battery, and I had a 1 ohm resistor in series, but I didn't show it in the previous clip, but it was there. And of course we have the magnet. The way this works is there's charge carriers moving along the surface of the magnet, perpendicular to the magnetic field. So it's going to experience a force F equals QV cross B. And assuming current is going that way, we have current V cross B gives a force F into the board. So that's going to cause the magnet to rotate this way, which is, I guess, going to give us a torque pointing up. I hope that's correct. That's how it works. I want to actually calculate the torque on this, and I've gone ahead and done that. So the force on a wire in a magnetic field, just F equals I L cross B, or written there in differential form. And I'm interested in the torque, not exactly the force. So torque equals R cross F, and substituting dF into that formula, we get dt equals R cross I dL cross B. And we're integrating from A to B. Now I'm defining point A to be the center of the magnet, right there. And I'm defining point B to be the end of the magnet at radius R. So that's what that is, and I'm integrating dt, so you get t. Now I don't really care about, okay, it's pointing up, so it's going to be in the positive z hat, whatever. But I'm mainly interested in the magnitude. And R, dl, and b, they're all, forgot something. Okay, R, dl, and b, they're all perpendicular. So I don't need that sine 90 degrees, whatever. Just I, B, R, dr. Also, I turned dl as dr, just so it would match up with the r. And integrating that, we get torque equals 1/2 I br squared. Or substituting I for voltage over resistance, we get that. Okay, so when you plug in all of the numbers, you're going to get an embarrassingly small torque. 10 to the minus 5, pretty small, but that's okay because the moment of inertia of the magnet is very small because the mass is very small and the radius is very small. So torque equals the moment of inertia times angular acceleration, and approximating the magnet to be a cylindrical disc, we could plug in I equals mr squared, or 1/2 mr squared rather, and if we solve for angular acceleration we get that it's 2 tau over mr squared. Plugging in the real world numbers, we get 1200 radians per second squared. So 1200 radians per second squared, that's quite a bit of acceleration. I probably got nowhere near that in the real world test just because friction, mainly the instability of the system itself. I mean, the magnet was like bouncing all over the place. But in theory, it should be pretty fast. So that's it. Take care.